Thank you very much. First, let me thank the organizers for inviting me here. That's my first time in Austria in a math conference. It's a very nice Schrödinger Center. It's a great conference. I'm going to talk about some results, part of them in collaboration with Daniel Cibotaru, about a very old theorem. Basically, I'm sure that most of us have thought about this. We learned it in school, and it's maybe a foundational result. This is why I was interested in it recently, and then yeah, I got some new results in the field. But I think more interesting is in this whole story, it's a 200-year-old problem. More interesting it is to see how things evolve and yeah, the different aspects. There are many aspects to this problem. So I will start by saying Gauss discovered his formula as an applied mathematician. He was in fact a public clerk. He had to do some actual measurements. And he was employed by an office of mapping the district of Hanover or the province of Hanover. And over there, the ground is very hilly. There is nothing easy about measuring. And apparently what happened was that Gauss at some point had to measure a region like that. And he noticed, of course, that when he computed geodesic triangles on these Hanover hills, at some point he got triangles with 3 right angles. So the sum of angles was not 180. Many people discovered that. However, Gauss, by spending maybe 20 or 30 years in the field, realized that he can compute the angle defect by looking at this triangle and taking the average of what is now called the Gauss curvature. So it's really an applied math problem. And apparently what Gauss didn't do was to try to compute angles in space, like to check if we live in Euclidean space or not. So although he had all the tools, apparently he didn't look at that. He didn't take large triangles, like geodesic in our ambient 3 space, and check if the sum of angles is pi or not. So let's start. My initial motivation was to compute the volume of an ideal hyperbolic 4 simplex. So if we have a 2 simplex, then the area is always pi. And if we have a 3 simplex, three ideal simplex, then okay, one of the vertices is at infinity. It looks like a prism, but then there is this part of a sphere inside the 3 faces of the prism. And the tetrahedron has 3 dihedral angles because they are 2 by 2 equal. This angle here and this angle here are equal. And the volume is given by this Lobachevsky function. This is the Cyrillic letter L from Lobachevsky. And it's a complicated formula for the volume. So I was asking myself, what is the volume for a 4-dimensional simplex? Yeah, maybe you know the story about this formula. It was done before there existed any model for hyperbolic geometry. It's very nice that people were able to do something like that. Okay, so now let's start with Gauss-Bonnet. The easiest instance of Gauss-Bonnet is this sum of angles in flat space is pi. But that's not the correct way of looking at it. You have to look at exterior angles. And there, the sum of angles is 2 pi. And then you notice the same stays true for any polygon. Okay, let's say it's convex. Okay, it doesn't matter how many edges you have. And I think this picture already appeared in Jean-Marc's talk. The correct way of looking at exterior angles is not that one. But here you take the orthogonals to the sides and you make a small exterior cone. That's the exterior cone. And you call this angle here the exterior angle. And now a rephrasement of the statement before is that the sum of the red angles equals to 2 pi. How how to see that in an extrinsic way. We call this sum minus 2 pi the angle defect. If the polygon is not flat, then there's going to be some defect. So how to see that? Let's just take the unit normals to each side. For instance, along this side, the unit normals are parallel and they are called E. Okay, so there are some unit vectors, so points on the circle. And I did the picture again. Now I draw the image of the map from the sides to the circle called the Gauss map. So to each point on a side, I associated the unit exterior normal. Okay, so this E here, for instance, is the constant value along this segment. Okay, now at the edges, you have more values. In fact, this angle here, 5, you can see it as the circle sector here. And now the sum of exterior angles equal to 2 pi is just length of the circle is 2 pi. Okay, good. So we have seen that it's good to look at the Gauss map, meaning the unit normal associated to each point. Let's now move to surfaces in R3. So to a small region drawn like here, A, B, C, D, I associate the image of the Gauss map, which is a larger or smaller spherical polygon. Okay, and Gauss defined his curvature as the ratio of the two areas, like infinitesimal ratio of the two areas. He takes a very small region, looks at its image on the sphere through the Gauss map, and divides. Okay. Oops, sorry. I meant to say here. He realized this can be computed intrinsically on the surface. Now, in a geodesic polygon on a surface, we have an angle defect, which is sum of exterior angles minus 2 pi. It should be 0 if the interior is flat. And the Gauss formula is the following, as I try to say here. You integrate the curvature on a, say, geodesic triangle, add the angle defect for the exterior angles, and the sum is 0. So this is a way of computing the angle defect. Good. I guess that should be clear. So these are the ideas that we try to do in higher dimensions, like these exterior angles. There are going to be now some exterior spherical cones, spherical polytopes. So now I will just say a few words about the history of the problem. The Gauss formula was generalized by Bonnet for triangles which are not, or polygons which are not geodesic. So in that case, Bonnet has a contribution from the sides, and his contribution is like a smooth version of this exterior angle. You see, these two vectors are not exactly the same. They compute some sort of extrinsic curvature or exterior angle. Okay, so in Bonnet's formula, you have the contribution from the sides. So far, the Gauss-Bonnet formula has contributions from 2 faces, 1 faces, and 0 faces. I mean, vertices, edges, and 2 faces. Good. Okay, and finally, the version we are used to liking is quite late, in fact. It says on a closed surface sigma. Unfortunately, sigma is supposed to be 2-dimensional in this picture, and x is 3-dimensional. So you take the total Gauss curvature on a surface, and the result is 2 pi times the Euler characteristic. But the correct way of seeing this, in light of what follows, is to take the area of the two spheres times half of the Euler characteristic. Why is that? Because if you view your surface as the boundary of some x is 3-dimensional, then easy topological argument tells us that Euler characteristic of x is half of the Euler characteristic of sigma. So here, in fact, we get Euler characteristic of x. This should be the more natural way of seeing the von Dijk formula. Okay, and so we have all the elements so far in dimension 2. Now let's move to dimension to hypersurfaces in 2n+1. So this is 100 years distance from Gauss, because it was very hard to find the analog of Gaussian curvature. So what happened? Like, this was the real breakthrough in the theory with Hopf. He realized that the degree of the Gauss map is defined as before. You have a hypersurface in an odd dimensional Euclidean space. Then you take the exterior unit normal, you view it as a map into the sphere, and you compute the degree. This degree will essentially compute the Euler characteristic. And the way to link this to Euler characteristic is by extending this vector field defined only on the shell, on the boundary. You extend it in the interior to some vector field with isolated zeros. And you ask the zeros to be of a special type, which is always possible by deformation. So they are radial in some directions and minus the radial vector field in other directions. Okay, and these are all the stationary points I like that. Here is an epsilon sphere around the stationary point. And you define a plus or minus 1 associated to each stationary point. And they compute the Euler characteristic of X, of the interior. Now, let's see how Hopf proves his formula. He says his basic construction is he extends the Gauss map G to the interior with the exception of these points, because he has to normalize the vector nu. So he extends to a vector nu, but this will have 0. So when you divide by the norm, there are singularities in these points. So V is not defined in these points. Nevertheless, you can pull back by the smooth map V the volume form from the sphere. And now, yes? No, sorry for that. Sigma is the hypersurface, and X is the interior of sigma. Sigma is the boundary of, yes, in an odd dimensional Euclidean space. Yeah, sigma is like the surface we see in the picture. And X is the interior, the handle body. Okay. So now you pull back the volume form from the sphere to X minus this finite number of singular points in the interior. But since you pull back a closed form, it stays closed. So you can apply Stokes on the interior with the exception of some spheres. Okay, so when you integrate, you take the degree of the Gauss map, you can in fact localize it around the singular points by Stokes. Because this step here is Stokes. The difference between the two would be the integral on this 2n+1 manifold of D of the form. But the form is closed because it's a pullback of a closed form. Yeah, it's really a very nice argument by Hopf. And in fact, he obtains the degree of the Gauss map is just the volume of the sphere times Euler characteristic of X. And as we said, X and sigma are related in Euler characteristic terms, but this is just half of the Euler characteristic of sigma. Okay. So what is the link? How can you express this in intrinsic terms first, and how to do it in not for hypersurfaces? So Hopf, I believe he realized that like the Gauss curvature times the volume form, also the pullback of the volume form from the sphere is intrinsic to the surface, to the hypersurface sigma. It can be expressed in terms of the metric on sigma. In fact, it's the Pfaffian of the metric. We'll see that. Okay, so I call this the Hopf egregium theorem, by analogy with the Gauss theorem. And in the case where 2n equal to 2, this thing here is just the integrand in Gauss-Bonnet. Okay, you can write it in terms of curvature like that. But in higher dimensions, we have to see exactly how it is. That's what we are going to do. Now, the computation is based on this observation. The Gauss map is an endomorphism of the tangent space. The differential of the Gauss map is an endomorphism of the tangent space. So we have our surface going to the sphere. So that's the point P. This is GP. This is G of P. So the Gauss map views as a function. And now the differential of this map goes from this tangent space to this tangent space here, but they are parallel, they are the same space. So really the Gauss map, the Jacobian of the Gauss map is an endomorphism of some space. And it's exactly the shape operator, the Weingarten operator. Because the Jacobian of the Gauss map looks at how the unit normal varies. That's the definition of second fundamental form, or shape operator. That's really just the definition. So the pullback of the volume formed by the Gauss map is the determinant of the second fundamental form, which is extrinsic. However, it can be also computed intrinsically because of the Gauss equation. When you have a Gauss equation, the ambient curvature is 0. So this computes your surface curvature in terms of the second fundamental form. And now comes the crucial part of my talk. Instead of this horrible expression, we can write it in a very short way. Yeah, so my talk and the work I'm talking about is based on this good notation that has been discovered and rediscovered by many people, which allows you to do computations with these objects, but without indices. If you start writing indices, you're lost. The computations are just impossible. So what do I mean by the square of the second fundamental form? Well, I write it, okay, upper and lower indices are the same for me because we're in Riemannian geometry. So the second fundamental form is this tensor, and I look at its square in the sense that this is an element in a tensor product of algebras, of Grassmann algebras or exterior algebras. So I take this EI will be multiplied by some EJ, and the EK with some EL, when I write again this term with J and L. Okay, so this should be essentially clear. I'll get also back to this a little later. Okay. So yeah, if we are happy with this, we'll see it again anyway. The question is now how to get the determinant of the second fundamental form from the intrinsic quantity, the square of the second fundamental form. So this square is intrinsic because it's just the Riemannian curvature on the surface. So how do we get the determinant of some matrix or some form from its square in this sense? Okay, and the answer is the Pfaffian. I'll define it carefully. So now let's see how to define Pfaffian. This is an exercise in linear algebra. That's an unfair exercise to give to your undergrad students. If they are not good in linear algebra, just ask them to show that the determinant of a skew-symmetric real matrix is greater than or equal to 0. You can do it with eigenvectors, but it's not easy for students. It's a little cheating because the reason is this determinant of a skew-symmetric matrix is in fact the square of a polynomial. So of course it is positive. So let me give examples before I define the Pfaffian. Sorry. So when n is 1, we have 2 by 2 matrices. The Pfaffian is just the variable. In 4 by 4 matrices, we have this expression, while the determinant has 24 terms here. And I also had a 6 by 6 example where it is also easy to compute the The Pfaffian, there are few terms. I forgot how many, but I don't know, maybe 6. Anyway, there are relatively few terms in the Pfaffian. It's a very nice polynomial because it has coefficients only plus or minus 1. You can define it over every field. Okay. Now, another piece of data, when you have a vector space with a volume form, let's say, there is this isomorphism between the top exterior power and real numbers given by, in this direction is multiplication by the volume form, in the other direction is erasing the volume form. This is called the Berezin integral. Okay. Now I'll define the Pfaffian of a skew-symmetric matrix. I first write it as a two-form, like here. It's the way you, from the shape operator, you go to the second fundamental form. And then the Pfaffian is just taking this form to the top exterior power and divide by n factorial. Okay, and we get the formulas I had on the previous slide. Namely, if you do the exercise for n equal 2, you will just get that, Ag minus Bf plus Cd. Okay, so the ingredients are taking powers in the exterior algebra and then erasing the volume form, dividing by the volume form. Okay, and there is, what is nice is that everything is invariant and no indices. Okay, now we get to double algebras or double forms. If you have two R algebras, their tensor product is also an algebra. Think about these algebras as forms in two pairs of forms. A and B are forms on a manifold. Okay, for instance, if A are differential forms on M and B are elements in the exterior power of the vector bundle E, then you can multiply objects like that. So most objects you work with in Riemannian geometry are actually double forms. For instance, a Riemannian metric is a 1-1 form. Yeah, it has a EI, Gij, EI, tensor EJ. Then the Ricci tensor is also that. And if you have a double form of some degree in the two variables, when you take the twisted exterior differential by some connection, you just increase the degree of a form in M, but not the degree on E. It's a form on E. Okay, so this is the construction of the Pfaffian of the curvature. Now it's a little more complicated. We have a bundle of even dimension with a metric and compatible connection. Then the curvature is a skew-symmetric endomorphisms. As we said, we transform this into a two-form on E. So the curvature tensor now becomes a double form of type 2-2. Yeah, it's not an endomorphism on E anymore, it is a form on E. So, we define the Pfaffian of the connection by taking the top power of the curvature, which is of degree 2n to n, and then divide by the volume form in the fibers, which is this Berezin integral. Yeah, it's invariantly defined. You can give local formulas if you want. Okay, and this is a so-called characteristic form. There are other types of characteristic forms which are considering R to be a two-form on M, tensor endomorphisms on E. So if you consider R in this double algebra, then the power K is not the one we had before. It is multiplication of forms in the first term and composition of endomorphisms in the second term. And then you can take traces. You make other types of characteristic forms. The Pfaffian is not like that. And let me show that the Pfaffian is a closed form. I remind you the formula. So the Pfaffian was just the curvature power n divided by the volume form in E. Yeah, this is a 2n form tensor, a volume form in E. I divide by the volume form of the metric H. Okay, so let's see the proof, because this is going to be the only proof of my talk. So by the second Bianchi identity, the curvature tensor is d-nabla closed. You take the twisted exterior differential. But now you write the curvature power n as the Pfaffian tensor, the volume form, because once you divide by the volume form, you're left with a Pfaffian. So this is what R power n is. But now the metric is parallel, therefore the volume form is parallel, and when you take d-nabla of this object, it's just d of the Pfaffian, because nabla on the second term is 0. Okay, so this... It is an 2n form. No, my manifold has no dimension n, 2n, has any dimension. The fibers, so it's a slightly more general setting. You take a vector bundle of rank 2n, but the base can be anything. Okay, so it is closed. If you take two different connections for the same metric, the difference is exact. In fact, every two metrics are equivalent, are isometric on a bundle. Okay. It is a natural form. When you have a map between manifolds and bundles, it pulls back. And now it has two very particular properties. If the bundle admits a parallel section, then the Pfaffian dies, because the curvature doesn't see one direction and it needs all the directions. Okay, maybe I'm wrong. Maybe this is only true for a top degree, when E has the same rank as the dimension of M. I guess. Or maybe not. No, I think, yeah, I guess it's true in general. Okay, and also, if there is a non-zero section, then the Pfaffian is exact. The cohomology class is 0. Okay, such properties are not true for the other Pontryagin classes. Okay. So now this is the this is the standard Gauss-Bonnet or Gauss-Bonnet Chern formula. So as I said, the history is very complicated. The formula says you integrate the Pfaffian form and you get this topological invariant. The formula basically is due to Hopf, but he only proved it for hypersurfaces. Then Allendoerfer and Fenchel extended it to surfaces in Euclidean space, but not hypersurfaces. Then Allendoerfer and Weil gave a full proof, but by using the tool of decomposing the manifold in polyhedral manifolds. And then finally, Chern gave an intrinsic proof, a very nice proof. In my preference, he didn't, but maybe he did. Yeah, I'll okay. Yeah. Or 38. Yeah. Apparently, he knew something, but yeah. Okay, so there is a more general formula that I didn't write, and one of the goals of my talk is to present this formula with a proof in the spirit of Chern. Okay, so now let's move to polyhedra and polyhedral manifolds. So a polyhedron, I guess most people here know what polyhedra are. They are just given by degree 1 inequalities in Euclidean space, or they are the convex hull of a finite number of points. When they are compact polyhedra or polytopes can also be defined by their vertices. Okay, so there is this object that you may have seen in Jean-Marc's talk. I think he drew something like that, this spherical sector. He did, but I paid attention because it looked like, okay. So you can do this for every face of every dimension or codimension. So when you have this triangle face, I have this blue triangle, which is all the unit vectors coming out of the face. Then for this edge, I think this edge here, I have such a spherical strip. And finally, there is a spherical diamond there. This is old, or I think it was introduced by Windgen in the 70s. It's called the Windgen cycle. Okay, so when we have a polytope, we look at the outer angles defined as all the unit vectors which are in these outer regions. When you take unit normals around faces at a point. Okay, so now let me just give such a horrible formula and explain what it means. So let's assume, okay, remember that the Pfaffian used to be exact if we have sections in our bundle. We have non-zero sections. Yeah, this was one of the properties. So when you have 0 sections, it is closed. When you have 1 non-zero section, it is exact. What happens when you have 2 independent non-zero sections, or maybe 10? So assume you have a family of unit sections in your bundle indexed by some manifold X, which could be a polytope, it could be a simplex. Anyway, it should be compact. Okay, then the Pfaffian is kind of L times exact in some sense. So let's see. I define a form of degree 2n minus L minus 1. So I go down L plus 1 degrees from the Pfaffian by integrating in X such a form defined on X cross M. So maybe the precise ingredients are not important, but they are local ingredients. This is the curvature of the manifold. This is the covariant derivative of the multi-section V, which is a double form. Then this is the derivative with respect to the parameters of the section. And finally, this is the section V itself. So these are all double forms. And you can multiply them. Their nice property is that they commute. Their degrees are so that, except for this V. So all the others commute because they have homogeneous. They have equal degree in both components. So whenever you commute, you get plus 1. So they look horrible, but they can be treated. Okay. So even for L equal to 0, this is a complicated term. And I repeat the definition here. I integrate with respect to X part of this form. And I'm left with a form on M. And the theorem is that each transgression is a primitive for the transgression of the sum of the transgressions on the boundary of the polytope. So you have a polytope of dimension L. It has many boundaries of codimension 1. You sum the transgressions on each boundary component, and the result is exact, and the primitive is given by the one higher transgression. Okay, and finally, the first one is a primitive for the Pfaffian when you have one section. Okay. Okay, because L equals 0, it means you just have one section. The polytope is a point. Okay, and this is actually the heart of Chern's paper, and that paper has been quite mysterious because the computations are not easy. His idea is very beautiful, but the paper is not easy. So now there is a proof for that, and I will just give some rough ideas. The Chern's idea is to consider a family of connections, but not on the base manifold M, but on the sphere bundle. So you lift everything to the sphere bundle. And over there is a good property of the sphere bundle. It has a tautological section. So you know your Pfaffian, when pulled back upstairs, will be exact, but Chern constructs the primitive. And he does it in this way. He considers a family of connections. One of them has a parallel section. And then you use the property that Pfaffian vanishes when you have a parallel section, and you use Leibniz-Newton, and you construct transgression. This is quite familiar nowadays. And the way to prove the transgression theorem, I was cheating when I stated it like that, is because there is an alternate definition. You just integrate the Pfaffian of such a big connection. Where is it? The big connection? Yeah, based from here, you construct a connection on a larger manifold, and you integrate it partially in the parameter space X and T. Okay? And in order to compute it explicitly, you compute the curvature, and then you notice that all these ingredients commute. So when you take powers, at first it seems hopeless, but in fact you can commute, and you know that Pfaffians die whenever you don't have all the vectors needed for a basis. So plenty of terms die, and little by little you eliminate them, and you're left with something computable. Okay, so this is the transgression theorem. And now, using that, you can prove a Gauss-Bonnet formula for polyhedral manifolds. So what is a polyhedral manifold? It is a topological space which is locally homeomorphic. So it's, I guess, a topological manifold. But the atlas is smooth, modeled on polyhedra, convex polyhedra. Okay, I guess, I believe this is standard. There is a notion of Riemannian metric, and there is a notion of outer cones for a polyhedral manifold that, again, I try to draw. Yeah, the outer cones is like what escapes from all faces. Like these are, yeah, what is okay. So, and these outer cones glue nicely, and they make a complex over your manifold. Yeah, so the lower your, for higher codimension faces, your the face corresponding to it in the outer cone increases in dimension. The higher dimension is for vertices. Yeah, but not here. Yeah, you have a metric. So you have a metric on each tangent space. Yeah. Okay. So now here is the Allendoerfer-Weil Gauss-Bonnet. They used it to prove the Gauss-Bonnet without boundary, but it's very nice in itself. Okay, so the difference between, there is a defect to computing Gauss-Bonnet by the usual formula in the interior, and it is given by contributions of all faces of every codimension and integrals over the sphere outer cones. And the integrals are of some locally computable quantities in terms of the metric, the curvature, the intrinsic curvature, the metric, and second fundamental form. Yeah, so they are just local ingredients for each face. Okay. So in principle, the formula is hard to use. Now, I wanted to say something about the proof. Maybe I'll just say about Chern's idea. Chern's idea is that when you take a vector field with isolated singularities and you divide it by its length, its graph becomes a manifold with boundary. And the boundary at a singular point is the sphere inside the tangent space there. So then you use again Stokes in order to compute the integral of the Pfaffian, and it gives you plus or minus 1 for each point. That's Chern's proof. Okay. So let me skip this. So yeah, there is an induction process of taking a unit vector, but it is not going to be normal to all faces because it cannot be orthogonal to two faces that meet somewhere. there is some correction. The correction will be some transgression. So there are sums of iterated transgressions, eventually giving the formula. There is also a Gauss-Bonnet in odd dimensions. It's the same, except that there is no more Pfaffian for the highest phase, but otherwise still contributions from all phases. And it can be deduced from the even dimensional variant. Now let's apply this to flat manifolds. Flat manifolds with totally geodesic faces. So I'm going to go back to the formula. So the formula implies the curvature of each face and the second fundamental form. These are complicated polynomials, but when they are zero, the result is zero. So in fact, nothing contributes except when the y's are just points. I have to interpret the formula in that dimension. And there, the formula is that for a flat polyhedral manifold with totally geodesic faces, the Euler characteristic is just the sum of outer angles, normalized with the volume of the corresponding sphere. So you can see this easily for a tetrahedron in R3. Yeah, let's say the outer angle at this vertex is the triangle that I try to draw above. Yeah, this geodesic triangle on the sphere. Yeah, so this arrow is this point, and so on. The outer angle is this spherical triangle, and in all the spherical triangles make up the sphere. That's why you have. Okay. There is an analog statement for constant sectional curvature. Now each face contributes, and there were some partial results by Santalo in the 70s and Sato, I think, in 2006, something like that, for the sphere. I think these formulas are hard to get by hand in high dimensions. It's hard to compute spherical volumes. Okay, now to answer my initial question, this ABCDE is an ideal hyperbolic tetrahedron. It has 5 vertices, and each triangle has a dihedral angle, because each triangle is codimension 2. Yeah, so there is a dihedral angle associated to each triangle. And the volume of the tetrahedron is just this constant, minus 2 pi squared, plus pi over 3 times the sum of dihedral angles, exterior dihedral angles of the two faces. Yeah, the vertices don't contribute because they have, their contribution is actually encoded in here. V is the number of vertices. V of m vertices, okay, the number of vertices of m is V of m. Number of vertices of y is V of y. Okay. Okay. They are at infinity. So they contribute like the outer cone, I guess it's half a sphere. Yeah, when you have very parallel lines, the outer angle is big. Yeah, so when you have something like that, the outer angle is very big. So when they are tangent, the outer angle is everything. Area of y, okay, so this is for y equal to triangle, and there are also contributions from y equal to vertex or zero face. They all have the same outer angle. This is why something like it's encoded in here. Okay, so now I'll get to the results with Daniel. Okay, So we define this odd Pfaffian for a Riemannian odd-dimensional manifold. There are some rational numbers. Okay. And then you also use the metric, which is a 1-1 form, not only the curvature, which is a 2-2 form, in order to cook up some form. This should be compared with the formula for manifolds with boundary. So when the polyhedral manifold is in fact modeled on the upper half space. Okay, and we have two types, actually, yeah, two big types of metrics and two particular cases. Let me just stay with the particular cases. When the manifold has small conical singularities, this is the conical metric modeled on some n Riemannian manifold n. Yeah, so it's usual picture of a cone. Then the contribution in Gauss-Bonnet is minus, I mean, the defect in Gauss-Bonnet is minus the integral on the boundary of the odd Pfaffian. And there is a similar formula when you have fibered cones or what is called edge singularities. Okay, and now when you have a large cone is something like that near infinity, so something which expands near infinity. Then the Gauss-Bonnet defect is plus the odd Pfaffian. And when you have fiber boundaries, which are this type of metrics here, there is a slightly more complicated, I mean, it's not more complicated, but it also involves the fibers of the, okay, of the fibration. Let me say that there are other people who studied this. I think Pierre Albin has some results in these directions. And I also learned from Mark that one of his students, actually his PhD is maybe earlier than our paper. He does the large and small conical metrics, right? Of course, here there are also asymptotics. We don't need to have precise cone metrics, but these are technicalities. So let me end by, these are the two references that I used. Thank you.